Okay, so let's look at these trig functions and see what we notice. Okay, so looking at this sine curve, I asked you to take those toothpicks and place it tangent, okay, to the curve. And looking at that little toothpick, how did the tangent lines, what is happening to my tangent lines? What are the slopes of those tangent lines? So where is the slope going to be 0? So at pi over 2, and it's because why? I've got a horizontal tangent line, right? At where else? Oh, yep. So the troughs and the bells. Okay, so that's going to be what? Negative 3 pi over 2, a negative pi over 2, a pi over 2, and a 3 pi over 2. So tell me something. So tell me, what does that mean if I plot this on my derivative curve? So like if I use this information and I graph the derivative, what does that mean that at each one of these points I will be doing? A what? Perfecto. So x-intercepts. So x-intercept at pi over 2 and x-intercept at 3 pi over 2, at a negative pi over 2 and a negative 3 pi over 2. Good. Okay. So where is going to be the slope of this graph? Where are my tangent lines, the slopes of my tangent lines here? Where are they going to be positive? Okay, so here, so at negative pi over 2, I'm sorry. Said negative pi over 2 and I started over there at negative 2 pi. So negative pi over 2 to where? To pi over 2, yeah. Okay. So negative pi over 2 to a positive pi over 2. Where else? Okay, good. So negative 2 pi to what? So a negative 3 pi over 2. So put a little union in between there, sorry. And then where else? So 3 pi over 2 to 2 pi. Okay, and that's just by looking at this graph. Remember, it's a periodic function, so it's kind of continuous all the way through. Okay. So where, and how do you know that the slopes are positive there? So what's happening to the graph? It's what? Increasing. Perfecto. So it's increasing. So it increases there. All right, so where is it negative? Kind of everywhere else, right? Okay, so where's that? So negative 3 pi over 2 to negative pi over 2. And then from pi over 2 to, so from pi over 2 to 3 pi over 2. And how do I know that? It's decreasing. Good deal. Good deal. Okay. So now let's graph the derivative. So let me change my color. So we got the x-intercepts of the derivative curve. But where is the graph going to be above the x-axis and where is it going to be below the x-axis? Okay, so it's going to cross the x-axis at negative 3 pi over 2. Okay, but what is going to happen from negative 3 pi over 2 to a negative pi over 2? What did we say the graph was doing? It's decreasing, so it's going to be where? Below. So it's going to look, it's going to be graphed under. Yep. All right, so what about from negative pi over 2 to a positive pi over 2? What is happening there? It's going to be increasing. Okay. And then what's going to be happening between pi over 2 and 3 pi over 2? It's going to be decreasing. And then what happens from 3 pi over 2 to 2 pi? It's increasing. And then what about this little piece over here from negative 2 pi to that negative 3 pi over 2? Where is it? It's going to be increasing. Okay, so tell me what this derivative curve looks like. Cosine, perfecto. Okay, so when you used your calculator, does that match? So using your calculator to do the derivative function in your calculator, the sketch is very, very much close to that. So that means that the derivative of sine of x is going to be what? Cosine of x. Awesome. Okay, so let's do the same thing with cosine. So where is the slope going to be 0? So negative 2 pi, negative pi, 0, pi, 2 pi. So that means that I am going to cross what? The x-axis at all of these values. Yeah? Okay, let's try to get the same colors. Did I use green for the increasing ones? I don't think I did. Who knows? Who knows? Y'all know I can't keep track. Okay, so where is the slope going to be positive? So what happens here? So it'll be positive between where? Negative pi to 0. And where else? So pi to a 2 pi. Good. All right, where is it going to be decreasing? So negative 2 pi to negative pi, and then 0 to pi, and then other places as well, right? And I know this because, why? It's periodic. Sorry, this like drawboard app is like so slow. And I know it because I've got my increasing, decreasing as periodic. It continues forever and ever and ever. Okay, so if I graph my slope function, so from negative 2 pi to negative pi, where is my graph going to be? So negative 2 pi to negative pi, the slope is what? Negative, so that means I'm going to be where? Below. All right, what happens from negative pi to 0? It's positive, so I'm going to be up here. All right, and then what happens from 0 to pi? I'm going to be negative, so I'm going to be below. And then from pi to 2 pi, it's positive. So I'm going to be up here. All right, so what does this graph look like? Negative sign. Okay, good deal. So a transformation and of negative sine of x. So remember, normal sine of x opens, goes up, right? So up this way and down. But this one is going to be negative. So the derivative of cosine of x is what? Negative sine of x. Good deal. Okay, so how can we find the derivative of tangent? Perfecto. So remember, tangent of x is just sine of x over cosine of x. So if I want to take the derivative with respect to x of tangent, then what rule can I use here? Quotient rule, yeah? So it's going to be the what? Quotient rule tells me I'm going to take what? How am I going to do it? So I'm going to take the bottom. So I'm going to take cosine of x and multiply it times what? Derivative of the top, which is sine of x. So what's the derivative of sine of x? Cosine of x. Minus the top, sine of x, times the derivative of the bottom, which is negative sine of x. Good deal. and this is all over the bottom squared. So I'm going to write it like that. Yeah. Ooh, yeah. Okay. All right. So if I simplify this, cosine times cosine is what? Cosine squared. So write it like this. Remember, these are all congruent. So if I write cosine of x squared, that's the same thing as me saying cosine squared of x. So those two things are congruent. Okay. And then a negative sine of x times a negative sine of x is a what? Positive sine squared of x. Good. All right. Can I simplify this some? Okay, what can I do? Okay, so cosine squared plus sine squared of x is what? 1. Perfecto. Remember the Pythagorean identity? So cosine squared of x plus sine squared of x is what? 1. Well, what is 1 over cosine squared of x? Secant squared of x. Awesome. So the derivative of tangent is going to be secant squared. Crazy. So we can prove all the other ones because all the other trig functions are just reciprocals of what? So, what did I just say? Sine. Did I say sine? Sine, cosine, and tangent, right? So they're just reciprocals of those. So we can prove them the same way, this exact same way, to show that they all are true. So let's kind of define all of these. So the derivative of sine of x is what? Cosine of x. The derivative of cosine of x is going to be what? Negative sine of x. The derivative of tangent of x is what? Secant squared. All right, what's the reciprocal of sine? Cosecant? Good deal. So the reciprocal of sine of x is cosecant of x. All right, this one's weird. Okay, so the derivative of cosecant, like I told you, you could prove it by making it 1 over sine and using the quotient rule. But it will be negative cosecant of x times cotangent of x. What's the reciprocal of cosine? Secant. So the derivative of secant, okay, let's think about this. If cosecant is that crazy multiplication, cosecant of x times cotangent of x, what do you think maybe the derivative of secant would be? So maybe a negative secant of x times a tangent of x. But without the negative, actually. So it's going to be secant of x times a tangent of x. And then what is the reciprocal of cotangent? I mean, tangent is what? Cotangent. Okay, so the derivative of cotangent, what do you think it's going to be? So if the derivative of tangent is secant squared, then maybe the derivative of cotangent will be what? So cosecant squared, but with a negative. All right, so let me point something out. Okay, so all of, this kind of helps you memorize it a little bit, but all of the derivatives of trig functions that start with a c, what do you notice about them? the derivatives of everything that start with a C, the derivatives are all what? Negatives. Okay. All right. All right, so take a second and answer these 3 or 4. Is it 4? I think it's 4. These 4 questions at the bottom. Okay, so let's look at these questions. So number 1, it was asking you to find the derivative of that function and then evaluate the derivative at pi over 3, right? So what is it actually asking you to find? What is that number, that negative 1/2? What is that? Good deal. Awesome. So slope of the tangent line at that point. Yes. So just making sure that you're understanding like what we're actually finding and what we're actually doing. Is everybody good with that one? Okay. Number 2. So number 2, find the equation of the tangent line here at x equals pi over 2. So it's one more step that we did in number 1 that then I actually have to find the equation of that tangent line. And this one actually is a horizontal line. Good? Questions about that one? You feel okay? All right, the next one, what rule am I going to have to use for finding the derivative here of x times tangent of x? Product rule. I am multiplying 2 functions together, right? My first function is x. My second function is tangent of x. Okay, so it's the first times the derivative of the second plus the second times the derivative of the first. Make sure you have the derivative notation. If you do not have that derivative notation and you just put an equal sign, I will count off. Okay, so get in the habit of writing that out. Good deal? Okay, questions about that one? Feel good about that one? Okay, now this one, I feel like this one's always crazy when we talk about the limit definition of a derivative. So let's remember what a limit definition of a derivative is. Remember there's 2 of them, right? So we have this one where it is the limit as x approaches a, so some value a where I take the original function and I subtract it from the function evaluated at a, all over x minus a. Yes, you could have simplified this, like you could have changed secant of x to 1 over cosine of x and tried to do some simplifying of this. But to me, the easiest thing is that it's in my limit definition of a derivative form. So what is going to be my function? My original function is going to be what? Secant of x, yes. So, and then the a value that it's approaching is going to be what? Pi, okay? Because think about this. What is secant of pi? Uh-oh. What is secant of pi? So it's going to be a negative 1, right? So that's why it turns into a positive 1 right there. Good? Okay, so now all I need to do is take the derivative of secant and then plug in a pi for x. So the derivative of secant of x is secant of x times tangent of x. Plug in your pi, and you're going to get a 0. Does that make sense? Okay. In the last class, I did have somebody that simplified it, and that's a-okay. Completely a-okay, and did some algebra to simplify it to make it work. But the easiest thing for you to do is to look at it and notice that it is the limit definition of a derivative. And you can look and you can find the original function, and then you can find what it is approaching. So what value it's approaching. Good? Does that make sense? I look a little stumped on this one. A little bit. Oh, because the derivative of secant of x is secant times tangent.